Hey there, ladies and gentlemen, boys and girls. Welcome back. Today we are going to talk a little bit about light waves and color. We're going to talk about what light waves are. We're going to talk about what is color, why do we see different colors, and why are different objects different colors. So let's start off with a little bit about what light waves are. All right, first things first. So I have two pictures here on here. The bottom one looks pretty complex, and this is what we call that's what a white or a light wave looks like. Right? Whether it's the light coming from the sun or from a light bulb or bouncing off of an object, the light coming off of it actually is two waves, one kind of in this direction, one in this kind of direction, that perpendicular. That's some pretty advanced physics, but this is what we call, or compared to everything we've done so far, which has been a mechanical wave. Light waves are what we call electromagnetic waves. They're electromagnetic, and the red wave represents the electric wave, and the blue one represents the magnetic wave. Not that you need to know the difference between them, but just kind of give you an idea of what we're talking about here. These are electromagnetic waves. I'm going to have to abbreviate here. All right. Electromagnetic waves. What does that mean? All right. Light waves are electromagnetic waves, which means they do not require a medium to travel. Medium is a fancy term for a material to travel through. Sound waves are mechanical waves. They require a medium, which means things like why sound can't travel through empty space. You saw in the last video about how particles have to bump into each other for sound to travel. That's a mechanical wave. In space, there's not particles really necessarily for them to bounce off of each other or pass to the next one, so it can't sound. So when you see the big explosion in space in the movies, understand that there would be no sound. You'd see the flash of light because light is an electromagnetic or a magnetic wave, which means it can travel without a medium. It can travel through space, which makes sense. Literally, we see the light travel from the sun through empty space to us on Earth. All right. So a mechanical wave needs a medium, the material to travel through. A light wave is an electromagnetic wave, which does not need a medium. All right. One thing that's also a little bit different about light waves, all right, that's different than mechanical waves, is about their energy. So when we talked about sound, we said that sound is based off of, or the energy of sound is based on the amplitude, how tall the wave is. So for sound, this was a really loud wave. And this was a very quiet wave just because of the amplitude. All right. Light waves are a little bit different. Light waves, the energy is directly related to the frequency. All right. The more frequency a wave has, the higher the energy. All right. So the frequency is going to determine the energy of the wave. So or waves that have more energy have a higher frequency, and vice versa. Waves that have a very short wavelength also have higher energy because of that inverse relationship between frequency and wavelength. All right. So now there are all kinds of electromagnetic waves in the universe, and we'll be talking a little bit about those when we talk about the electromagnetic spectrum. But the one that you are probably most familiar with is visible light. By visible light, I mean literally every color, every light you have ever seen in your entire life or will ever see falls in a very, very narrow range of frequencies and wavelength. Anything too far on one side, we can't see it. Anything too far on the other side of frequencies, we can't see it. There's a very narrow range. In fact, out of all the waves in the universe, we only see about less than 1% of the waves in the universe with our eyes. So everything you've ever seen is just a fraction of the things that are out there. Which is a little mind-blowing, but we break down basically all of the things we see into different colors. That's how our brain interprets light waves, and each color is different from one another. All right. And they're all different based off of the amount of frequency and wavelength. So here are basically the colors that we know. All right. Each one's a little bit different here. So for example, we start at let's start with the very bottom there. You notice that it's about 650 to about 700 nanometer wavelength. It's very, very small. All right, nanometer. It's about a thousandth of a milliliter or a millimeter. Any light wave that has that wavelength and thus that frequency, our brain will interpret as the color red. Anything with about 550-ish, 500, 575 wavelength, our brain will interpret as the color green. And anything about below 450, so things with really high wavelengths with higher frequency, our brain interprets as the color purple or a purplish color. Let me shrink this down so I can get my tools here. All right. So, kind of recapping what I just said there. Let's pick that. There we go. Oh. All right. So, right, the ones that have a very, very short or very, very long wavelength, right? All right, are going to be more of the reds. Now you notice that it goes up in a specific order. It's a spectrum. All right, spectrum means a gradual change. We go from red to orange to yellow to green to blue to indigo and violet, or our good friend Roy G. Biv. All right, all the way up here we have ones that have very short wavelength. Well, if that's the case, then we know based on that this is short wavelength, means very high frequency. This means very low frequency. All right. And based on what I just told you about light waves and energy levels, you can also determine that these ones up here, these colors are a little bit higher energy level. And abbreviate energy as NRG. And down here would be lower NRG. And I do have the expectation that you know the difference between them, like which color has a longer wavelength, blue or orange. Think about it. Which one has a longer wavelength, blue or orange? The answer is orange. Right? Which one has higher energy, yellow or indigo? Which one has higher energy? The answer is indigo. All right. And so you actually see these in laser pointers. If you ever had a laser pointer, you notice most laser pointers, like with a little pen, most of them are red. They're not, although you should never put them directly in your eye, they're typically low energy. All right. You want to get some really good ones, a little bit pricier, you can get green laser pens, but those are a little bit stronger ones. And you can't really buy without a specific reason. There's only specific places where you can buy ones that give off a purple light. And those ones are very dangerous because they are the highest energy, more likely to cause damage to individual cells if you were to point it in their eyes or in their soft tissue. It wouldn't burn through their hand or anything like that, but you could really hurt somebody with a violet laser pointer. All right. So then it goes to this idea about why we see different colors because our brain interprets different wavelengths of light. But now the question is, like, why do some things appear certain colors? And the question is, well, what if what I see is red is actually blue? And I'm going to tell you right now is scientifically, there's only one answer. So you see right here, starting at the bottom there, we have a red object, white light, which is made up of all the colors. White light is all the colors mixed together. When it hits it, notice only one of them bounces off. Notice only one color. Where's my, there we go. Only one color bounces off. So let's say I have my eye here. It's a good looking eye. All right. When that red light bounces off of it, it's going to hit me in the eye. My brain is going to interpret one wavelength of light. And that one wavelength of light is red. All right. While compared to, say, up here, this object is going to let bounce off all the colors. And so when all the wavelengths of light hit my eye, my brain interprets that as white. So things like the second one, the green one here, this is like plants. Plants we see appear green because they absorb or take in all the wavelengths of light except for one. They reflect or bounce off green wavelengths. And thus, that's why when we look at them, we see that green wavelength and it appears green. While black, on the other hand, absorbs all of them. And our eyes interpret the absence of light waves as black. You don't believe me? Close your eyes. It doesn't turn white or brown, it turns black. All right, it turns black because there is no light hitting that eyeball for your brain to interpret. So the object's color depends on what colors are reflected and what colors are absorbed or taken in. It's also why it's a bad idea to wear a black shirt on a really hot day. That's white light is coming from the sun, and it's going to absorb all that light energy, make you really warm. You should wear a white shirt because it's going to reflect all that energy. All right. So, we talked a little bit about what is a light wave, electromagnetic wave. Its energy depends on frequency. We talked a little bit about different colors, or the different colors are based on their wavelengths and frequency. It's how we interpret different colors. And then finally about why we see objects as different colors, because some wavelengths are bounced off, reflected, and some are taken in or absorbed. And whatever hits our eye is what our brain interprets. Make sure, if you didn't feel like you understood any of those things that we talked about, make sure to go back and watch the video again. Otherwise, thanks very much for watching, and good luck, and may the science be with you.